Hi guys. Hacker Cup 2024 practice round is about to end actually. I thought the problems were quite nice, especially the last one. So I'm making this solution walkthrough video. So as you may have seen here, I'm filming it while the contest is live, but I'll upload it just after it finishes. So yeah, let's let's jump right into it. So problem A. Problem A. I mean, you can read the problems. I'll post a link to this site in the description where you can read the problems, or you can just listen to me explain them on a whiteboard. So those are the options. So problem A is essentially a variant on a classic problem. So let's go over here. So problem A is you have n people, and the n people need to get across a bridge, essentially. And you have they have a flashlight, so whoever's crossing the bridge needs to have the flashlight because it's dark or whatever. Um, And so whoever's crossing needs to have the flashlight. Either one person can cross at a time, or two people. So let's say one person crosses the bridge, then if one person crosses the bridge, that one person has to cross back to bring the flashlight back so that everyone else can cross. But so two people could cross the bridge, then one of them could bring the flashlight back, uh, then one of them could cross again, and so on. Right? So each person I can cross the bridge in SI seconds. So each person has a time that they need to cross the bridge alone. But also, two people can cross at the same time. And if they do that, one of them gets in a wheelbarrow. So one of them gets in a wheelbarrow and is basically pushed by the other person. So the person on foot is the person whose time matters. So if you're pushing somebody, apparently that takes exactly the same time as if you were just walking alone. So that's how it works. And we want to know how long it takes for all these people to cross the bridge. Minimum time. Actually, they're asking whether they can cross in k seconds. So we want to know whether these n people can cross in k seconds. So let's just take one of the examples. We have 1, 2, 5, and 10 as the times. So there are four people, and that times that they need to cross the bridge are 1, 2, 5, and 10. And so these four people need to get across this bridge. Yeah, beautiful bridge. So how do we solve this? So what the problem essentially is saying is that either one person can cross, in which case we take their time that they need, or two people can cross, in which case, the slower one should be the one that gets in the wheelbarrow, right? Um, that's a reasonable thing to do because then the faster one's time is taken into account. So that means if two people are crossing, we take the time of the faster one. They take the time of the faster one, which is the difference between this and the classic bridge crossing problem, where it's exactly the same, except if two people cross, the slower one is the one whose time matters because the faster one has to wait. So in this version of the problem, the solution goes something like this. First of all, we can just say since the faster person is the one whose time matters, it sort of makes sense to take the fastest person in the whole group and have them crossing a lot because their time will be the one that is taken into account. So the fastest person should cross along with somebody. Let's say in this case, the person who needs 1 second and the person who needs 2 seconds cross. maybe it's minutes. I don't know what the unit is. Let's just say it's seconds. Then the fastest person crosses back. Then again, the fastest person takes somebody else. So in this case, 1 and 5 cross. Then the fastest person crosses back with the flashlight and the wheelbarrow. And then the fastest person takes the last person across. So this is what this looks like. Each of these trips will take 1 second because that's the time the fastest person needs. And so they've crossed in 5 seconds in this case. And so that's the general fastest way for everyone to get across is if the fastest person just runs back and forth with the wheelbarrow and just takes a person each time they're on the starting bank and just runs across, dumps them onto the other side, and then runs back. And yeah, I mean, why is that the fastest? You can prove that relatively simply by saying that how many crosses will this take? Right? If there's one person, it will take 1 crossing. If there are 2 people, this will still take one crossing, right? Because person 1 will just cross along with person 2. If there are 3 people, this will take 3 crossings. Because 2 of them will cross, 1 of them comes back, and then 2 of them cross again. If there are 4 people, it'll take 5 crossings. And it's pretty easy to see that this is how it'll go from there. So this is the minimum number of crossings you need. This is the minimum number of crossings you need for each number of people to get everyone across. And this strategy we have that we've developed here will use this minimum number of crossings, but also each crossing will be as fast as any crossing could possibly be. It'll take the time of the fastest person. So that's just an easy way to show that you can't do this faster because you're using the minimum number of crossings and each one of them is as fast as it could be. So yeah, that's this problem. So the solution in the end ends up being that you take this minimum number of crossings, which is 2n minus 3, unless it's 1, unless n is 1, in which case it's 1. So you take this minimum number of crossings, multiply it by the fastest person's time, and just check if that's less than or equal to k. So that's problem A. Yeah. Cool. Moving on to problem B. Problem B, line by line. So, yeah, this is probably the least interesting problem, in my opinion, in this problem set. Let me write the problem names on here. Okay. So in problem B, we have somebody writing a piece of code, essentially, to solve a problem. And so they have to write n lines. And for each of those lines, they have a p% chance of not making a mistake in that line, so writing that line correctly. And they succeed in solving the problem if all of the n lines are correct. So, yeah. And these probabilities are independent. So, instead, they can try and increase the probability that they get this problem right, essentially, by doing one of two things. They can either reduce the length of their code to n-1 lines, because, I mean, if they reduce to n-1, then they're more likely to get it right if the probability still remains at p, that each line is correct. So they can spend some time finding a slightly better solution that reduces their code length from n lines to n-1 lines, with still a percentage of p, a probability of p% for each line being correct. Or they can leave it at n lines, but increase p. So they can increase the probability that each line is correct by writing the code more carefully. So they can just spend that time writing the code for longer. So the question is pretty simple. How much would you have to increase p by in this second solution, in this second option, so that these two are equivalent in the sense that they both produce the same probability of solving the problem? So what's the minimum amount you need to increase p by so that this right-hand option is at least as good as the left-hand one? And so what do we do here? I mean, this is option 1. This is option 2. Let me use a different color for that. This is option 1. This is option 2. And so for option 1, the probability that you get all the lines correct is just, I mean, let's create a, instead of working in percentages, let's work in just numbers from 0 to 1, so that we can multiply them and everything without having to worry, because percentages just divide over 100. So instead of p%, let's just say we have some number q. Wait, let's just use lowercase p for this. This is uppercase p. So lowercase p is between 0 and 1, let's just say. And so in option 1, it's just p to the power of n-1, right? That's the probability of getting it right. And in option 2, if we increase the probability from p to some q, to some value q, then we get q to the power of n. And so we want to equate these, and yeah, we want to find q, and so q is just p to the power of n-1 over n. Since everything's positive, obviously, and whatever. So yeah, q is p to the n-1 over n. So all you do in this problem is you take the p in the input, which is between like 1 and 99, I think. You divide that by 100, so you get a float in this range between 0 and 1. Then you raise that to the power of n-1 over n with just float standard library operations. And then you multiply that back by 100 to get it as a percentage. And then you subtract the original p in the input so that you get the difference in percentage. That's all it is. Yeah, that's all the time I'm going to spend on that. My solutions will be in the description, by the way, the code, in case you want to check that out, in case you want more details. So problem C, this is more interesting. This is more interesting. So let's dive into it. I'm going to again explain on the whiteboard. Problem C. So we get we get a bunch of coordinates essentially. Let me actually change this background because this is going to be helpful. So we have a 2D plane where the axes are specifically doesn't really matter in this problem, so I'm just not going to draw them. We have a 2D plane, and on the plane we have some points, integer coordinates. So let's say crosses are probably better for this. This, this, something like that. So we have a number of points, and we want to find these are ants. These represent ants on a plane, and we want to find the minimum number of them we have to move so that all of them are on some straight line. Yeah. So that could be this line, that could be any line that goes through. Just any straight line. So what's the minimum number of them we need to move to get them all on a straight line? But there is a catch, right? I mean, not a catch. It's the other way around. There's something that helps us because this is actually a very difficult problem, and especially given the constraints, because we have up to 1 million points with huge coordinates. We have up to 1 million points that we need to consider. So we are the problem is made easier by the fact that if the answer is m, right? So in this case, the minimum number we need to move is 2 because we already have these 3 on a line. And so we need to move the other 2 to get them on the line, and that's the best option. So in this case, the number we need to move is 2. But so the problem is made easier since if the minimum number that we need to move is 2, is m, let's say, then the answer that we print needs to be between m and 2m. And as long as that's satisfied, then it's considered that we got the problem right. So we need to print between m and 2m as our answer. So that sounds initially kind of weird and random, but it actually does help a lot. So why does that help? Well, for instance, I mean, first of all, let's look at why this problem is difficult, right? In this problem, you could have why this problem is difficult without that extra help that we can print any value in some range rather than the exact value. Because, well, if you have loads of points, let's say you have 1 million points, the largest number you can have in the input. What we need to find essentially is the highest number of points on one line, right? The max number of points on one line, because n minus that will be the answer. The largest number, the fewest number of points we need to move is n minus the largest number of points that we don't need to move. So we need to find the largest number of points on one line, the line with the most points. So the issue with doing that exactly is that if we have 1 million points, and let's take the example that no triple of those 1 million points is on one line, except one group of 3, right? So this group of 3 that we drew earlier, that we highlighted earlier, is on one line, but no other group of 3 is. No other tuple of 3 is. What that means is that we need to find these 3 points on one line because we need to distinguish between, in this case, the answer is whatever n is minus 3, I mean, okay, if we're finding the max number of points on one line, then that's 3 in this case. But if one of these 3 points wasn't on this line, so if we had no triples on the same line, then that value would be 2. So since we need to distinguish between these two, we need to somehow find these 3 points on one line. So in the case where we have 1,000,000 points and only one group of threes on a line, we need to find that group of 3 or identify whether or not it exists. And that's very hard to do quickly. So that's not going to happen. But so how does this between M and 2M business help in this case? What's happening? Something stopped working. Did everything stop working? Okay, now we're back. So the answer that we print has to be between M and 2M. So in this case, right, the number we need to move would be n minus 3. So as long as we print something between n minus 3 and 2n minus 3, we're fine. This is a pretty big range. So this helps us. Notice how this implies that, for example, if the answer we choose is n, if we just say n is the number of points you need to move, then if m is at least n over 2, then we just got the problem. We just solved the problem. That's correct. That'll be judged as correct. So we can print n if we have to move at least half the points, right? Because that means n will be between m and 2m. So if we determine that at least half the points need to be moved, then we can just easily print n and that's it. So what does that mean? That means, well, m being at least n over 2, that's the same as n minus m being at most n over 2. But what's n minus m? N minus m is the max number of points on one line. So if the max number of points on one line is at most half the whole number of points, then we can just print n. But this is the difficult case, right? This is the case where there aren't many points. There aren't many big lines. So this is the difficult case, and we can solve it as long as we identify that it is that case. So this means that all we need to do is find whether there is a line with more than n over 2 points on it. All right, so I just realized you couldn't see this because my face was covering it. So well, let me just say that again. So we can print n if m, the number of points we need to move, is at least n over 2. Because in that case, n will be between m and 2m. But what does this mean? This means n minus m is at most n over 2. This is equivalent to that. So in this case, if n minus m, which is the largest number of points on one line, if n minus m is at most n over 2, then we can just print n. But this is the difficult case here. So this is where the largest line is at most half of the whole number of points. So all we need to do is find. So if there is a line with at least n over 2 points on it, well then we need to find that line. And there can only be one such line, right? Because I can actually say strictly greater than n over 2. And there can only be one such line. That's pretty easy to see. Because two such lines can only share at most 1 point. And so if there is a line with, actually, yeah, that means there could be two such lines, but both of them would be the same length. And that length would be n over 2 plus 1, essentially, if you round down. So if there is a line with more than n over 2 points, we need to find the line. We need to actually find the biggest line. But otherwise, if we determine that there isn't such a line, we can just print n. So this is like a get out of jail card in the sense that it saves us the difficult cases where there aren't any lines with a huge number of points on them. So we just need to find whether there's a line with more than half the points in the whole problem. And that's easier to do if we use something called randomization. So that basically tells us that if we take, so for this part, when we're trying to find the line with more than half the points on it, if we take two random points from the endpoints, then if there is such a line with more than n over 2 points, right? If there is such a line, then the probability that both of these points will be on that line will be at least a quarter. Because there are more than n over 2 lines. There are more than n over 2 points on that line. So if we take two random points, and those 2 points will define one line, right? Because all points are distinct, all pairs of points are distinct. So if we take two random points, they have at least a quarter probability of being on that on such a line that we're trying to find, if such a line exists. So if we just do this repeatedly and just consider all the lines that those pairs of points define, so we could take a pair of random points. So take some pair. That pair defines a line. Go through all the points in the whole all endpoints. Check if more than n over 2 of them are on that line, or just find how many of all the points are on the line, and we do that for, let's say we do that k times. We do this, like take a pair, go through all the points, check how many are on the same line. We do that k times. And now we consider the line that we found with the most number of points on it. If there is a line with more than n over 2 points, the probability that we don't find it, right, is the probability that we don't find it on any of the turns, which is the probability that we don't find it on a single turn is at most 3/4. And on k turns, it's that to the k. So the probability that we don't find it is less than this. And so if we choose a sufficiently large k, this will be really small, basically. And so if we choose, I mean, we have 1,000,000 points, right? But that doesn't matter in the sense that it doesn't change this probability, but it changes our time complexity, because our time complexity is basically k times n. Because for each time we do this, we go through all the points and check if each one is on a certain line or not. So since n is around 1,000,000, I think the value of k I take is like 300 or something. Let me check actually. Doo-doo-doo. So the value of n I take, yeah, 300. The value of k I take. So I use 300 tries, and so this probability is 3/4 to the 300. The probability that you don't find the point is 3/4 to the 300, and that's tiny. That's just, that's not going to happen. So what are we doing? We take k random pairs of points. For each pair, we go through all the points, find how many are on the line defined by those 2 points. Then we take the maximum of all of those k times that we did that. And then if the number of points that we found is more than n over 2 on one of the lines, then we just print n minus the number of points on that line. That's how many we need to move to get the rest on that line. Otherwise, we just print n, since the number of points on the biggest line is at most half the total number of points, we need to move at least half the total number of points. And so if we print n, that'll be accepted. So that's problem C. That is problem C. So I think that was an interesting one. That was a nice one. So now we move on to problem D1, right? And so D1, D2 are both problems with the same theme. It's just D2 is harder, as would be suggested by the ordering. And so let me explain the problem. Actually, it might be useful to use that diagram here. Yeah, this is nice to look at visually. So we're playing curling, essentially, but it's one-dimensional, so we're just throwing things left to right. So we have n balls. They're called balls, right? Stones. N stones. They're being thrown from left to right on this number line. So they're all thrown from 0, and they're all thrown with a certain energy. So the first stone here, for example, is thrown with energy 9. And so if it doesn't hit anything, it'll stop at 0.9 because it's thrown from 0. So on each turn, it moves to the right by 1, and its energy decreases by 1. And when its energy is 0, it stops. That's if it doesn't hit anything. So in this case, we throw a stone with energy 9, it stops at 9. We throw one with energy 5, it stops at 5. Next, in this case, we throw a stone with energy 7. And so it comes forward, this blue one, but there's a stone on position 5 in its way, right? So it hits that stone. And so if there is another stone at the same position as you stay where that stone was. So you stop. And the other stone moves off with the same energy that you had. So you just give it your energy, essentially. You swap energies. So that's what happens here. So then this green stone keeps going with the blue stone's energy instead, and it stops here at 7. So that's how this works. And so we're told that there are end stones, we're given their starting energies and the order in which they're fired, and there is some target on the board. I mean, in this case, it's at 1, but there is some integer coordinate. Everything's in integers, by the way. Thankfully, there is some integer coordinate that we're interested in, and we want to know at the end of this which stone is closest to that integer coordinate. So the stones are numbered in the order they're fired. So the first one is this red one, the second one is the green one, the third one is the blue one. And so in this case, the target is at point 1, and so the blue one, so stone 3 is the closest to the target. So yeah, there could be 2 stones at the same distance from the target, or multiple stones, many stones. In that case, we're just interested in the one with the smallest index. So we just need to print an index and a distance. That's what we need to print. Okay. So yeah. So how do we find this? So the first thing to notice is that the indices can be ignored throughout the problem, because if we just go back to the diagram here, the order in which they're thrown, so stone 1, stone 2, stone 3, and so on, that's the order in which they will be on the board, because no 2 stones ever swap places. So stone 1 will always be the rightmost stone on the board, and stone n will always be the leftmost stone, and so on in between. So if we find the set of positions, or the multi-set of positions, because I guess you could have repeats, if we find the set of positions of all the stones at the end of the problem, then we know how to assign indices to that, because we can just sort those positions and then index all the stones from the back, right? Stone 1 will be the one that went furthest, stone 2 will be the one that went second furthest, and so on. So observation 1 is that indices will always be n, n minus 1, n minus 2, so on, 1, if you look at all the stones from left to right. And that's pretty obvious. I mean, yeah, that doesn't seem helpful initially, but coupled with observation 2, it's pretty helpful. And the second observation is that now that we're ignoring these indices, right? So let's ignore the indices now. We just need to find the final set of positions. We just need to find positions. But when doing that, we can do something pretty useful, right? So what is that? Let's consider a stone being thrown. So we have a bunch of stones here. Let's say a black one and a red one. And we're throwing a purple stone. So these colors represent indices. So we're throwing this stone, it starts at position 0, and it comes this way. Then the purple stone stops here. The black stone keeps going instead. But then the black stone hits the red stone. And then the red stone keeps going. And then the red stone ends up here, let's say. So what you'll notice is that since when a stone hits another stone, the energy receives is the energy that the first stone had, and vice versa. That means that the point at which this red stone stops is the same point at which the purple stone would have stopped if no stones were in its way. So that's just the energy of the purple stone with which it was thrown. So the red stone will stop at that point. So now the position changes between these stones are quite complicated, right? This black stone goes here, the red stone goes here, the purple stone goes here. But remember what we set up here is that the indices don't matter. So we don't really care which stone is which stone anymore, because the stones are interchangeable at this point, because we don't care about indices. We'll just map them back onto the indices at the end. So now if I redraw this whole thing, but without any colors, because we don't care about colors anymore, we started off with, let me zoom in a little more. We started off with stones here, here, and here. I mean, this stone is sort of a virtual stone. It's about to be thrown. And we ended up with stones here, here, and here. Well, if we don't care about which stone is which stone anymore, all we see that as a new stone appeared at this point. And that point it has the same coordinate as the energy of the stone that was just thrown. So that's just how the game works. If I now throw another stone with energy that would land it here if there were no stones in its way, that other stone would actually land here, and this stone that's over here would actually move to the right and end up being here. But we don't have to look at it that way. We can just say that if we ignore indices at this point, then one stone hitting another stone and the first stone stopping and the second stone moving off with the same energy that the first stone had, that is now equivalent to the first stone just passing through the second stone, if we don't care about which stone is which. So if we now look at the problem in terms of stones simply just passing through other stones, then it becomes really simple. It's just every stone is thrown with a certain energy. It stops at the coordinate with the same value as the energy with which it was thrown. And so it's actually very easy to find the set of positions of all the stones at the end of all this throwing. But so we said it's very easy to find the indices if we've found the positions. And now we've said that now that we don't care about indices, it's very easy to find the positions. So we just do that. We take all the stones, the energies that they get thrown with, that list will be the list of positions of all the stones at the end of the game in some order. It'll be a shuffled order, but it will be the list in some order. So we can then map the indices that the stones will have onto that list of positions by sorting the list of positions in decreasing order. So we take the largest position and give it to index stone with index 1. We take the second largest position, give it to the stone with index 2, and so on. Right? There could be ties, but that doesn't matter. And that's it. That's how we find the position of each stone at the end of the game. And once you know that, it's trivial. You just go through all the stones and literally just find what they ask you to find. The one closest to the goal. So that's it. That's this problem. That's problem D1. That is problem D1. So you might think that problem's quite cool. D2 is the more difficult version of that problem. So now we're going to go and talk about D2. D2 is interesting. So it has a lot of similarities with the first with D1. the only difference, pretty much, is that these stones now have a width of 1. So in the previous version, these stones were tiny, and you could have two stones in the same position. And so if a stone collided with another stone, the the stone that was initially moving would stop at exactly the position that the previously stationary stone had, and the stationary stone would move off with the energy that the first stone had. But now, since these stones are actually big, they have a width of 1. When one stone hits another stone, it'll the second stone will move off again with the same energy, but this time the first stone will stop one position further back. So let's draw that. So if we have a stone that was over here, then if you launch a second stone at it, the second stone will stop here, and this stone will move off that way, which means that the final positions will look like something like this. So the new stone will end up one to the left of the position where the original stone was, if they make contact, that is. So that is the only difference. But the energy transfer still works the same way. So that means let's look at the example they have on here. So the first stone is thrown with energy 8, and it stops at position 8. So still works the same way. The second one is thrown with energy 7, actually, so it stops right before it. Nothing happens. They're stationary. But then the third stone is thrown with energy 9. And the third stone obviously hits these two. So third one, this blue one, transfers its energy to the second stone and stops itself at position 6, just before the second one. But then the second one cannot move to the right because the first one is directly to its right, so it stops straight away. And then this one moves off to the right with the energy that the blue stone had remaining, which was 3, because it was thrown with energy 9. And so the red stone will move 3 spaces to the right and end up at 11. So this is what will happen. So they have width 1 now. That's how this game works. Yeah. So that's how this game works. So the first thing to realize is relatively simple, is that the indices observation from the previous version of the problem still carries over. So we said that if we just find the set of positions of all the stones at the end of the game, the order, we can determine the order in which those positions will be, because the stone that went the furthest will be stone 1, and the second furthest will be stone 2, and so on. So again, same thing applies. We only need to find the multi-set of positions, the list of positions of all the stones. We don't really care about the order that they're in. Right? But since the stones now have width 1, we cannot just do the swap. The swap that we were doing in the previous version, where if a stone was here and another stone was coming towards it, we could just pretend that they passed through each other, because the moving stone would stay where the stationary stone was, and the other stone would move off in the same way that the moving stone would have. That doesn't hold anymore, because the moving stone now stops one space before where the stationary stone was, and the stationary stone still moves off with the same energy, but now it starts 1 to the right. So there's essentially a +1 -1 exchange going on there, compared to the previous version of the problem. So we cannot just swap. We cannot just swap in the same way that we did in the previous problem. So what should we do here? I mean, let's take an arrangement of stones. I'm going to zoom in even further here. Let's take an arrangement of stones. So let's take some setup. Right? Let's take something like this. So this is the current state. You can have stones next to each other. You cannot have stones on the same position this time, just because they have width 1. So that's not how it works anymore. Okay. And so now we have a new stone that's being thrown. I'm just going to color it in to symbolize that it hasn't been thrown yet. This is position 0, though, so it's being thrown from here. One thing I forgot to mention, by the way, is that we're guaranteed that all these stones are thrown far enough that they won't stack backwards and like fill the slot from which we're throwing. So you can imagine if they were all just thrown very lightly, let's say all of them were thrown with energy 2, then from position 0, one of them would stop at 2, the next one would stop at 1, and this one would move off, then the next one would stop at 0, and this one would move off, and at that point, it's just undefined behavior. So we don't want the stones to go negative or whatever. So yeah, all the stones you're guaranteed that won't happen, basically. So back to this. What happens here? So let's say this stone is thrown with some energy E. Where does this go? So let's say it moves to the right. It'll collide with this stone, right? This stone will then move off with the next stone. The next stone will hit this stone over here and stop just before it. This stone will hit the next stone. And so this stone won't move at all. Then the next stone will move off. Let's say it has enough energy to reach the stone after it. And so it'll stop just before it. That stone will move off. And let's say that stone doesn't have energy to reach the next one anymore. So let's say that stone goes here. Right? So this is the setup that we end up with. And so what's the mapping here? Again, the leftmost stones... Wait, no. That's not what happened. This stone came here. This stone came here. This stone stayed where it was. So each stone that moved went just before the index of the stone after it, the position of the stone after it. Or if it didn't have enough energy, it just stopped where it stopped. So this is a pretty complicated mapping, right? There's a lot of stuff going on. There's a lot of movement. So how about instead of this mapping, we imagine we just change the mapping, essentially. Because again, like we said, we don't care about indices in this problem anymore. So we don't actually care which physical stone is which physical stone. We only care about the set of positions that we have. In this case, it actually is a set of positions. It's not a multi-set because you can't have the same position for two stones. So let's change the mapping. Let's change the mapping to this. This stone goes here. This stone goes here. So we're essentially doing the same thing that we did in the last problem, where if two stones come into contact, we say that the stone that was moving is the stone that keeps on moving. And that's equivalent if we don't care about which stone is which. So these mappings are still the same. So now every stone that we touched, every stone that this launch stone touched, seems to have just simply moved back by one, right? That's the new setup that we have. and with this new mapping. So every stone moved back by one, that every stone that we touched, and this stone that we launched just landed somewhere. And every stone to its left moved back by one, and every stone to its right stayed where it was. So that's that. That's the new way we'll do things. So let me erase these red arrows actually, so we can see what's happening a bit more clearly. So this is what it looks like. Okay. So this is simpler to deal with in terms of if we look at the positions where everything goes, but it's still quite weird, right? Because if we have this set of positions before this go, we have to find how many stones we jump over. We have to move all of them back by one. We have to slot ourselves in after those stones and repeat, right? So uh, we could do this, but it feels difficult because we need to have this set of positions. We need to be able to binary search in it, but also um, when we binary search, have the number of stones that we've hit and whatever. It's a bit complicated, and it ends up being too slow essentially. So what we let's keep going. Let's see how we're gonna look at things here. So for each stone that we had on the board before the stone was launched, it's interesting to see whether or not we'll reach that stone, obviously, right? So will you hit that stone or not? So for this stone, we know that this stone ended up reaching the first 4 stones, right? And what do I mean by reaching? I mean that even if you came into contact with that stone, then you've reached it. Even if you just came up to it and stopped and touched it and ended up being stationary right next to it, I'm still calling that reaching. Um, and so if we reach a stone, then within this mapping, in this purple mapping that I've drawn, you end up swapping positions. So you end up to the right of that stone. So if you reach a stone, that stone moves 1 to the left. So if you're thrown and there was a stone here and you end up stopping right next to it, we're going to say that the stone that was here actually moved back 1 and you ended up to its right. So that's how the mapping works. And so the energy to reach a certain stone, let's say we have some stone I, right? Let's say this is stone I, and it had position xi before the stone was thrown. So this is position 0. This is 1, 2. I'll number the positions at the top. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 15, 20. So these are the positions. This is x. So xi in this case is 11. It's at position 11. So will this newly thrown stone reach this stone? I mean, how do we see that? So if there's no stones if there are no stones in the way, right? If we're at position 0 and this stone is at position 6 in this case, to reach this stone we need an energy of 5, right? Because we need to stop right before it. So in this case, it's if we have an energy, if we have stones in between though, they sort of act as boosters, right? So if we have this stone at some position in between, then this stone gives us what a boost, a little boost, in the sense that this stone will stop over here, but then this stone will move off with the same energy, but from one position to the right. So actually here we need xi minus 2, or 4 energy, to touch stone number 6 with another stone. So 1, 2, and then 3, 4. We need 4. And you've probably guessed by now that if we have 2 stones in the way, it's xi minus 3, and so on. So each stone in between you and another stone gives you a boost of 1. So you need 1, the energy you need to reach that stone is 1 less. So the energy you need to reach stone I, is xi minus which number stone the ith stone is from the left. So in this case, this stone is the first one from the left, ignoring the stone we haven't thrown yet. So from the stones on the board already, it's indexed from the left, 1 based index. So in this case, it's the first stone, so it's xi minus 1. In this case, it has 1 stone to its left, so it's the second stone on the board, so it's xi minus 2, and so on. So that's the formula for the energy we need to reach a stone. That's the formula we need for the energy we need to reach a stone. And so all the stones that we reach, right, their positions will decrease by 1 in this version of the problem where we map the stones between goes in this way that I've drawn on the screen here in purple, the mapping in purple. Every stone that we reach, so if we reach it, its xi will decrease by 1. This is just me writing down how the board will change after a stone is thrown, right? That's what happens. And then we add a new stone at some position. Yeah, that's how the board will change. New stone. At position, the energy, the current energy of the stone thrown, plus I don't need an xi here, plus the number of stones reached, right? Because each stone that you reached will give you a boost of 1. That's where this new stone will slot in based on our mapping. And so now the energies to reach each stone, how will they change? This is interesting, right? So the energies to reach the stones that we touched, right? That we reached, their x's have decreased by 1. So if your xi decreases by 1, their number from the left hasn't changed, their index, because there's no stones that have been added to the left of them. So the energy required to reach them will decrease by 1, right? Because we have a minus 1 delta here and a plus 0. No change here. So the energy required to reach them, let's just call that R, that will decrease by 1 for this stone. But now let's look at the stones that we didn't touch, the stones to the right. Well, their positions didn't change, their xi's didn't change, but their number from the left, their index on the left, did change. They're now, that index is now 1 higher because we have a new stone to their left. So this won't change, but this will increase by 1, and since we're subtracting it, the new energy needed to reach them will decrease by 1. So if we don't reach a stone, the number from the left, will increase by 1, and so R will decrease by 1 either way. So the energy you need to reach each stone on the board will decrease by 1 as you throw this new stone. Because just intuitively, for the stones that you moved past, their position has now gone down by 1, so they're 1 easier to reach. And for the stones that you couldn't reach, well, their position's still the same, but you now have 1 extra booster stone in the way, on the way, pretty much. So that's how that works, right? Okay. So the energy you need to reach them will decrease by 1. For every stone, and now you have a new stone added as well. That makes keeping track of the energies you need to reach every stone pretty simple, because instead of decreasing them all by 1, you can just keep in mind that they will decrease by 1. So that makes life easier. But trying to start coding this at this point is actually a mistake, because this problem is it has a lot of inherent beauty, essentially, that we haven't yet discovered. So what's the value that we add? That's an interesting question now, right? So we have a bunch of energies we need to reach each stone, which are their position minus their index on the left. What's the new position of the new stone, right? The new position of the new stone was, like we said, energy plus the number they reached. That's the new position of the new stone. The energy the stone had plus the number of stones it reached. But so now, what's the energy that we need to reach that from the next stone throw, right? So we now need to consider this. We now need to add this to the list of stones that we have, and for future information, we need to know the energy we need to reach that. So what's the R value for this stone that we just added? Well, Ri, like we have up here, is xi minus the number from the left of I. And so in this case, well, xi, we have xi over here. This is the x. So this is the energy with which it was thrown, plus the number it reached, the number of stones it reached. Minus its index from the left. But what's its index from the left? That's just the number of stones it reached plus 1, right? its index from the left is the number of stones it reached, plus 1, because all the stones it reached, it jumped over. So minus number reached plus 1. And so these cancel. And we just get EI minus 1. So we decrease all the R values by 1, and the new R value we add is actually independent of everything, of all the R values we already have. So although the new position that we're adding, so we have the new position of, although the new position of the new stone is dependent on how many stones it reached, right? This R value, the energy you need to reach that stone for future stones, that's actually independent of the number of stones it reached. It's only dependent on the stone's energy, which is pretty cool. So what does that mean? That means essentially, so we're decreasing all the R values by 1, and then we're adding EI minus 1. So I mean, let's just add it before we decrease instead. So what are we doing to the list of R values? We're adding EI to that list, and then we're decreasing all of them by 1. So that's a pretty simple transformation that we're doing to the R values. And so what ends up being quite nice is that these R values are quite easy, are very easy to keep track of. And actually, they can be used to recalculate, or they can be used to determine the positions of all the stones, right? So let's take a look at an example where I show you what's going on with these R values and why they're actually helpful. So let's just take a look at an actual example. So we have some positions: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How big should we go? Something like this, right? So let's say we throw a stone. So we'll write the operations here. So initially there's nothing, then we throw a stone with energy 8. So that stone will end up at position 8. That's pretty simple. But alongside this whole thing, let's keep track of the R values. What were the R values? The R values were the energies we need to reach each stone. So in this case, it's 7, because we add the energy of this stone, which is 8, with which it was thrown, and then we decrease that by 1, so 7. And the intuition behind that is, for the next stone, if we want the next stone to reach this stone, it will need an energy of 7, because that means it'll end up here and it will reach the stone. So that's what that means. Pretty simple. Now let's throw a stone with energy 5. This stone, again, stops at 5. This stone's at 8. Everything's simple. Now the new energy we need, now the new energy value that we add, the new R value that we add, this is the list of R values, is 5, right? It's just the energy. And then we decrease both by 1. So we now get 4 and 6. And what does this mean? This means, so the list of positions, I'll write those here actually. The list of positions, 8, now they're 5, 8. But so we need, the R values are again energies we need to reach each stone. So the R values again are energies we need to reach each stone. And so we need an energy of 4 to reach this first stone. And we need an energy of 6 to reach the second stone, because if we have 6, then this one booster stone on our way will help us along to 7, to position 7. So now let's throw a third stone, and let's make it interesting. Let's throw 10. Right? So what will this do? This first stone will end up here. The second stone will end up here. I mean, the third stone, the one we just threw, will end up here. The next one will move all the way to here, and the last one will keep going and stop at 12, because it got 2 boosts of 1 each. So now the new list of positions is 4, 7, and 12. 4, 7, and 12. The energies now, again, we just add the new energy, so 10, and then we decrease them all by 1. So it's 9, 3, and 5. So as you see, again, these energies are correct. So the order is no longer correct because of the way we messed with the order up here, because we changed the mappings, right? We changed the mappings. We changed which stone we're actually calling which stone. So the order of energies is now different. This 9 doesn't correspond to the 4, and this 3 doesn't correspond to the 7, right? So here, this value doesn't correspond. These lists, the orders don't correspond, but they correspond in some order. So in this case, the 9 corresponds to the 12, the 3 corresponds to the 4, and the 7 corresponds to the 5. And so, redo. And so, yeah, these energies are still correct. You need 3 energies to reach the first stone. You need 5 to reach the second stone, because the first stone will give you a boost, so it'll get you to 6. And you need 10, and you need 9 to reach the third stone. So everything is correct. And so if you keep doing this, right? Let's say we're done. Let's say there were only 3 stones. This is where the cool part comes in, right? This whole problem is about positions. We care about the positions of the stones. So these energies to reach, these R values, are some quite arbitrary thing that we've just brought in. But they're very easy to keep track of, right? We just add the energy value of the next stone and decrease everything by 1. So these R values are very easy to keep track of. Albeit they will be in a different order to the positions, but we don't care about that, because whatever order we have the R values in at the end of the game, we can still restore the positions from the R values. And how do we do that? Well, obviously the R values we have will correspond to the stones on the board in sorted order, right? So the energy to reach the leftmost stone on the board required will be the smallest energy in the list of R values. So 3 in this case. So if we sort these R values, so in this case we'll have 3, 5, 9. We can now easily return and get these p-values from R values, right? Because now that we know for each stone how many stones are to its left, because we've sorted them, we can now recall that Ri equals Xi minus. So the energy you need to reach it is the position minus the number of stones, the index of the stone from the left. And so we can now rewrite this in terms of x. And now Xi is just the energy you need to reach it plus the index from the left, 1 based. So if we add for this list 359 of our values, now that we've sorted it, if we add 1 to the first one, 2 to the second one, and 3 to the third one, we get 4, 7, 12, and that's the sorted list of p-values that we needed. So this is quite a powerful thing where we needed in the position in the problem to find the positions at the end of the game of all the stones, right? But we translated that into a different something else that we're keeping track of, which is this list of R values, and they're very easy to keep track of, and then we can easily translate them back at the end. So, the main reason that this is the case is because that these R values are not changing orders in the way that the P values are. And so, what will this final list of R values be? I mean, you don't actually have to perform these additions and subtractions in this order, like we said. You can just say that for each energy, right? So at every initial energy of each stone will be added to this list of R values at some point, and then 1 will be subtracted from it some number of times, right? So for the first stone 1, it was launched with energy 8 and ended up with energy 5, and it was decreased 3 times. The second stone, it was only decreased twice, and for the third stone, it was only decreased once. So it'll just be decreased n minus the index of the stone if you take the 0-based index that many times. So for every stone, we just take the multiset basically of its energy plus its index minus n. If you want to make this 1-based, you can subtract 1. Yeah, let's do that actually. I mean, you can do EI plus I minus n, which looks nicer. Okay, let's leave it like this. So if you use 0-based indices, then this is the multiset of R values that you'll end up with. So you just chuck all of these values into some sort of vector or array. Then if you sort these values, you'll get the sorted list of energies at the end of the problem. So you take these, you sort, and then you add the index to each one. And that's it. That'll give you the list of positions in the game, like it did in this example. And so, yeah, the reason I say multiset, by the way, is because 2 stones can have the same energy required to reach them if they're right next to each other, right? Because if you have a stone here and a stone here, if you reach this stone, you're essentially also reaching that stone because you're jumping over both of them and ending up here in this place. So yeah, this is a multi-set, but the final set of positions is a set. So yes, that's the formulation of this problem that makes it very simple. So you don't need any data structures that are crazy or anything, and it's pretty nice. You can even make this final calculation slightly nicer by removing this minus n factor. So these EI plus I minus n values, right? They're the energies you need to reach each stone. But this minus n is just everywhere, right? So uh, it won't actually change much. So if we actually, in the end, what are we doing? So we're adding the index back as well for each stone. But so we've sorted these values in increasing order, left to right, and added that index back. But actually, if we sort them in decreasing order instead, because these stones will be numbered from the right, so these stones will be numbered in decreasing order by position. So the smallest index will have the highest position. So if we sort them in decreasing order instead, then instead of adding the index back, in this case, we'll be adding n minus the n plus 1 minus the index if we do 1-based indices. And so that's what we'll be adding. And if we just convert this to 1-based as well for a second, so we have this, I'll just do this in brackets, minus n plus 1. Now it's just become pretty simple in the sense that we have a set of EI plus I minus n plus 1, and we're adding n plus 1 minus the index back. And since this n plus 1 is constant, we can just reformulate this as taking the set of EI plus I, the multiset, sort that in decreasing order, and subtract, so add minus the index, so subtract the index. Subtract the new index, and now this is nice because it doesn't matter anymore whether the indices we use are 1-based or 0-based as long as they're consistent. So EI plus I here, and I here. It didn't matter in the previous version of the problem either. We just have to change this constant that we had to either n plus 1 or n. So yeah, that's how simple this problem is. If you want to implement it, you can literally just put these values in some sort of data structure, like a vector, sort them in decreasing order, subtract the indices, and then, yeah, just do the same thing we did in problem D1 at the end, where we just find the one that's closest at the end, very simply. So the implementation of D2 is actually just as simple as that of D1. So I thought this problem was very nice. It was a good problem. So yeah, that was fun. While we were talking, I believe the contest ended. I didn't expect this to take this long, but maybe I underestimated the time I'd take, which is probably expected. But yeah, this was fun. I did end up ranking 14th. Nobody above me or me got to fail the tests. last year was more chaotic in that sense, in that regard. But yeah, so those are the problems. Since the contest is over now, I can upload this live stream once I'm done. I mean, it's a video. It's a private live stream. Yeah. So that was fun. I just liked the problems in this contest. Um, I thought they were nice, so wanted to go through them. Yeah. Um, so thank you for watching. Let me go back to the. Whoa, you can zoom out, see all the problems. That's pretty cool. So yeah, thank you for watching, and goodbye. My code will be in the description.